Well, just as there are two faces on this coin, there are two types of motion. There's the motion that moves the coin up and down, and then there's the motion that spins the coin. Rotational motion and translational motion is what they would usually call it. Well, let's start by drawing something like a football. Let's say this football was spinning. And we're going to have it be spinning in this direction, essentially counterclockwise, if we were looking at it. And by using the right-hand rule, let's see, the right-hand rule would be something like this. Notice how my fingers are curling this direction, and my thumb is pointing that way. This is where the W is going to be. This is going to be the angular velocity. Angular velocity. Excellent. This is something we've defined before. There's a couple different ways that we can write this. Let's start by drawing our little piece of a pie from before, and let's look at the let's define what these are as theta right there. Keeping in mind that when this is starting to spin, this is imagine this is spinning here on its S. Once it starts to spin, obviously there's a velocity associated with this, the change of the S over time. That's the velocity. It would be tangential velocity right here. Okay, and we have two different ways that we can describe angular velocity. This is the speed of something spinning. One is to say that just simply W equals V over R, or I believe that is correct. Okay, and then we have, and this is tangential velocity, and then we have over here, another way to write this is that W is equal to d theta over dt. So that's just the change of theta over time. So similarly to what the tangential velocity would be, the change of this arc length over time, and then over here, this is the change of the angle over time. So these two things, the velocity and the angular velocity, those two things, tangential velocity and angular velocity, are sort of moving at the same speed, essentially. But, and so that's why they're really, really similar. That's why they even have almost the same name, tangential velocity, angular velocity. But you can see how they're slightly different. This one's the change of the arc length, and well, this is the change of the angle. So, great. Now let's maybe expand this a little bit. So W equals d theta over dt, which again, I like to write this as maybe the average. So again, this is the instantaneous, and this is the average, and then this is 2 pi over t. This would be the time that it takes, time that it would take it to spin around, you know, the entire circle. That's how much time it would take, and that's the velocity. Great. So this is how we can sort of describe angular velocity. Now, hopefully remember back from our kinematic equations from the beginning what those were. We're going to do almost the same thing over here. Let's start with the simplest one. W equals W naught plus a t. This is angular acceleration at this point. We'll come back to that in just a second. But notice how this is very similar to velocity equals initial velocity times, well, acceleration times time. It's almost the same equation. All we have to do is just slightly change these variables from v's to w's, essentially. Okay, and now let's go ahead and do what we did before, which was square the top. Okay, plus it should be 2a, and then we just have the change of the angle this time. Instead of the change of x's, we now have the change of the angle. This is how we can represent this. And then we go down to the next line, which would be, we start changing the angles down here, 0 minus x naught, blah, blah, blah. And then here we have to integrate. So plus t, and then 1/2 a t squared. All right, this is alpha right here. So you can see again, from here we square it, and from here we do an integral, and then at the bottom we can simply rewrite this. Instead of w naught, let's use the final w minus 1/2 alpha t squared. That's simply, if you don't know the initial velocity, but you do know the final velocity, then you can sort of rearrange these equations slightly by using plus or minus, etc., etc. And then the final version down here is going to be this one, 1/2 w naught plus w t. And this is almost as if we were sort of to rewrite this particular thing as a w t, but there's a half right there, 1/2 w t. I don't know. You just kind of have to want to visualize this, rewrite this in some sort of a way. Great. So these are just the simple rotational kinematics. Rotational kinematics. These are the rotational kinematic equations that you might need to be able to solve problems with this type of stuff. Angular velocity, rotational kinematics. Well, now let's describe this alpha. So alpha, if this is the angular velocity, let's try to increase the angular velocity. That would mean in the alpha, we need to go this direction as well. This would be things speeding up. Speeding up. But let's say we wanted to decrease the angular velocity, we would need the alpha going in this direction. Alpha going in this direction would slow it down, right? If that's the velocity going that way, and we have the acceleration going this way, it's going to slow things down. This again has to do with the right-hand rule. Notice it is rotating counterclockwise. Okay, the right-hand rule is pushing it counterclockwise. And so, hey, if this was rotating the other direction, spinning clockwise, then the W would be going this direction. So you just want to always use the right-hand rule. So if it was spinning clockwise, that would be, let's say, if we were looking at the, what is clockwise in? Clockwise would be this direction, yes? So it's rotating clockwise. You can see that the W would be pointing that way, because follow my fingers, right? Follow the fingers. But if the thing is rotating counterclockwise, you're going to notice that the W pointing this way. That's my thumb. This is the right-hand rule. The thing is rotating along your fingers, the right-hand rule. And so whatever it is, and so let's say it was rotating, I don't know, into the wall, spinning this way, like I was saying, Shazam, you can see how that would be going that direction. So anyway, the right-hand rule. Now, like, we can describe alpha in a couple different ways. Remember that the regular alpha, RA, like we say this, this is acceleration. This is regular acceleration. And then, so I guess this is tangential acceleration. So tangential acceleration, that would be similar to the tangential velocity over there. That's going to be equal to r, that's the radius, and times the alpha. And this is going to be angular acceleration. All right, so we've got angular velocity and angular acceleration. We can even describe this as dw over dt. That's going to be the instantaneous version, and delta w over delta t. That's going to be the average version. A couple different ways to rewrite the angular acceleration. Just keep in mind that all the alphas we've been talking about here, alpha, alpha, those are all angular accelerations. These are all the same acceleration. The only acceleration that's different is going to be this one. This AT right here. AT. That is tangential acceleration. And all the other ones and all the other equations are alpha. That's going to be angular acceleration. That's tangential acceleration. Now we can move on to rolling. Rolling is very interesting. Let's say we had a ball, and it started at this initial height right here, bam, and it was rolling down this hill and ended up over here. Let's say we had a ball doing like that. This was rolling down. We can say that there's like this vcom. There's this final velocity over here. This is vcom, where the center of mass of this thing started here at this initial height, and that's going to be equal at the end of this path down, c plus 1. This is a 1. Number 1. Okay. Number 1. Great. So what is C? C is actually just going to be based off of the constant of inertia that this object would have. So in this case, let's say this was a ball, a sphere, then the constant would be 2/5 for the ball, and so you put that plus 1. All right, and then this is the initial height over here, and so initial height. Great. So we have this whole situation. The ball starts here, ends up there. We can figure out what the final velocity at the bottom of this hill once it's done rolling down the hill. There's a neat little trick. Now here's where things start getting really confusing, because now we have to keep in mind that this ball has two kinetic energies. It's going to have the regular translational kinetic energy, which is the one that's moving this ball from here to there. You could follow this arrow down because it's going from here all the way down to there. That is the kinetic energy that would be regular old translational kinetic energy, 1/2 mv squared. And then we also need to include the rotational kinetic energy because it's also spinning around. It's also doing this. So that's going to have another type of rotational kinetic energy. Now, let's try to define these. The initial, the first one was going to be Ke, this one. I'll go ahead and make this red, regular old red Ke. This one is going to be kinetic energy is going to be equal to 1/2 mv squared, as usual. Okay, but what if we had the rotational kinetic energy? That's going to be this one, KER. That's when something is moving. That's going to be IW squared. That's when something is spinning. Okay, so these two things are actually the same. All right, it's very weird. They're different and yet the same, because this kinetic energy is when something is moving. Moving straight, mind you. It's got to be moving straight, in a straight line like that. Okay, and so this ball is moving in a straight line like that. However, another type of kinetic energy over here is one if it is spinning. If it's spinning, then it's also going to be moving like this. Bam. But there's going to be times when both of these things are exactly the same, and so we'll have to be very careful when we use these. So we'll take a look at some different examples of that. So we don't, for example, we don't want to use the kinetic energy if something is spinning but it's not moving. So if something's spinning but it's not moving, like for example this little football, if it was moving through the air and spinning, then it would have both the regular moving kinetic energy and the rotational kinetic energy. But let's say it was just spinning and it wasn't moving through the air, it was just spinning. In that case, it would only have rotational kinetic energy. And so that's why these two energies, they're both very similar. They're like the same, and yet they're not the same. And so as long as the object is moving, it's going to have kinetic energy, but it depends on which one it is. So we don't want to use this one if it's not moving. It's really important. If it's not moving, you're not going to use this kinetic energy. And if it's not spinning, you're not going to use this one. So you just have to know when you're not going to use them and when you are going to use them in order to know if you're supposed to combine the two together or not. Are you going to add these two kinetic energies together because both of them are present? Or do you only need one of them because only one of them is present? That is really the test that we need to start getting really good at. If you need to identify what the kinetic energy of an object is, you got to know whether it's going to have the rotational kinetic energy and the translational kinetic energy, or which one it is. So we're going to go through a bunch of different examples to figure out which is which. Okay, so before we go into that, we're just going to sort of draw a line here. Let's just make a note that if the kinetic energy of rotation is actually equal to 1/2 mv squared. Okay, so if you just happen to make a calculation of the kinetic energy of rotation over here, and you happen to notice, hey, wait a minute, that's actually just mv 1/2 mv squared. It could be that that's it. You don't really need to use the regular kinetic energy, because it could, like for example, for pendulum, if you start to try to say, hey, maybe the pendulum has both, and then you start, okay, well, it's 1/2 mv squared for the kinetic energy, then you want to add in the rotational kinetic energy and you calculate that, all of a sudden that's also 1/2 mv squared, and you're like, wait a minute, maybe I should double check this. Double check to make sure that your calculating is correct. It could very well be that that the spinning ball is gonna end up with the same, 1/2 mv squared, and it's moving, and so they're both gonna be the same exact 1/2 mv squared. It could be possible, but just double check. Double check to make sure that it's not like a pendulum where the rotational kinetic energy is the same thing, or like the orbiting around a move, where like those two things where the kinetic energy, um, the rotational kinetic energy equals 1/2 mv squared. That is the kinetic energy, and you don't need to add in the regular kinetic energy. So that's just kind of a note that you might need to keep track of there. So let's just start looking at some examples of what things have only kinetic energy. For example, over here, let's see, it would have to be only moving. So moving only. This is going to only have kinetic energy. All right, but none of the other ones. Let's say there was just a ball, all right, that was not spinning. All right, the ball has to be like flying through the air, the flying ball, but you just have to keep in mind that it's not spinning. So it's not spinning. All right, if it was spinning, then it would have both kinetic energies. But if the ball just moving like a knuckleball, just moving through the air, it's not spinning, it's only going to have kinetic energy. Let's say we had a block that was sliding across the ground. Sliding block. That's going to have only kinetic energy as it slides across the ground. Let's say we had a guy, a person running or moving. A moving person. Well, that's only going to have kinetic energy, unless somehow they're like twirling around. They're only just moving straight. Okay. So that's the type of examples where we would only have kinetic energy. If something is only spinning, a spinning only, then it's only going to have rotational kinetic energy. It's not going to have translational kinetic energy. Let's get some examples of that. Here is potentially like, I don't know, a top. Looks kind of weird, but that's a spinning top. Spinning top. But here's the catch. It has to be still in one place. It can't be moving, so it's not moving. This top, usually tops move around, but the top would have to be completely still. Okay, so that's just kind of one example. If it was moving, if it was spinning around and started to move, then that top would have kinetic energy. That's why there's some here where it was like, oh, well, in that case, if the ball is spinning, then yes, and if the top is moving, then yes, color coding. It's important to color code. Here's another example. Let's say we had two cogs. Here's a cog wheel here and another cog wheel here, and these two cogs obviously have their little spikes and stuff. So let's say we had two cog wheels spinning. Those obviously are not even moving at all. Those are only going to have rotational kinetic energy. Let's say we had a fan. Oh my gosh. Let's say we had a fan, and the fan was spinning. Well, there's another example of an object that would only have kinetic energy, rotational kinetic energy, or KER. Let's say, and here's some kind of stranger ones that are a little bit controversial. All right, so let's say something was, let's say you had a planet, bam, and something was orbiting this planet. Well, then it would only have it would sort of have this rotational kinetic energy of orbiting, this orbiting kinetic energy, KER, orb. All right, and here, I'll mark this in green, actually. I'm going to call this the orbiting kinetic energy, because it's a little bit ambiguous. This particular object may also have rotational kinetic energy, okay? Because it is spinning. That planet, like the moon, well, I don't know whether the moon would be spinning. There might be some catch there. But normally with most planets, it's going to be like spinning around and orbiting. So, you know, let's take a look at, for example, a globe. Here's a globe, a spinning globe. This, if the globe was spinning, globe spinning on the axis, then basically it would have the rotational kinetic energy of the axis. So there's going to be rotational kinetic energy orbiting and the rotational kinetic energy of the axis. Okay, if you're just spinning around the axis or whether you're actually orbiting around the planet, those are two different rotational kinetic energies. And so we're sort of going to be separating those out. Let's say you might have, I don't know, a swinging pendulum, for example. Just the pendulum swinging back and forth. That would have rotational kinetic energy, and you'll actually calculate it to be exactly the same as um, as translational kinetic energy if it was a pendulum. This is just a pendulum swinging. So that is the kinetic energy. Like, that's why you don't want to add both of them. So that's a little bit complicated there. And then let's say you had a yo-yo spinning. A yo-yo spinning. The yo-yo spinning by itself, just sitting there, would actually have rotational kinetic energy. And then here's the catch, though. All right, yeah, so let's just think about this. You might be asked to only find the orbiting kinetic energy of this particular object right here, which would be orbiting planet. But let's say you wanted to combine both the spinning on the axis energy and that one. So you would have to add both of these together. That would give you the total kinetic energy. Okay, total kinetic energy of these particular objects could be orbiting plus the axis. Okay, but it's a little ambiguous whether they're asking you for one on the left or the one on the right. You kind of have to know. And then let's say the yo-yo was swinging and spinning. If the yo-yo is swinging and spinning, then it's going to have two kinds of rotational kinetic energy. An object can have two kinds of rotational kinetic energy, both in the orbiting one, which would be this one, the orbiting of the yo-yo's orbiting. If it wasn't a pendulum swinging and it was a yo-yo, both swinging and spinning. So it's swinging and it's spinning. Swinging and spinning is going to give you two kinds of kinetic energy of rotation. So spinning and swinging. Let's not say orbiting, let's say swinging. So that's going to give you like so many different kinds of kinetic energies. Like, you just have to be very careful of which one you're adding together in your equations. So that's why it's a little bit difficult here. And then let's also figure out when something might be moving and spinning. There's more, but we're not done yet. Let's say again, this football right here. Let's say the football was actually going through the air and it was spinning and it was flying. So then in this case, this football would have both the total of the KE plus, oopsies, let's try to one more time here. This is going to be KE plus KER. All right, so the total energy is equal to KE plus KER in this particular situation. All right, sometimes it's equal to only a bunch of different rotational kinetic energy. Sometimes it's equal to rotational and the translational kinetic energy. Gosh, this is getting so complicated. So let's say we had a screw. Here's a screw, and that's being screwed into a wall. this direction and it's being rotated. So it's both rotating and spinning and moving. So that's going to be both the moving kinetic energy and rotational kinetic energy. And let's say I was tossing up that coin in the beginning. That coin was spinning through the air, so the coin had rotational kinetic energy, and it was also moving through the air, so it also had regular kinetic energy. So that was one situation. This is just a coin toss. Coin toss is going to have both regular and the rotational kinetic energy. And then we would also have a rolling object, okay, a wheel that's just kind of going in this direction and the wheel is turning. So I guess a wheel rolling. Okay, so rolling objects, rolling objects, rolling objects are going to have both. Moving and spinning objects are going to have both. Yeah. So that means that, I mean, if we were to put this in the math, again, you just want to add these two together. So this would be, yeah, the math is a little bit, there's a whole screen of math, so it's a little bit complicated. Anyway, hopefully this is relatively helpful. Now that we can figure out this rotational kinematics, we can figure out angular momentum. That's what's coming up next, which is just like there's two different kinds of rotational and translational kinetic energies. There's also going to be rotational and regular momentum. So angular momentum and regular momentum. Gosh, this is where physics starts to get really complicated when you start spinning things around. My head's starting to spin. So anyway, hopefully your head doesn't spin too much. Make sure to click that like and subscribe to my channel and all that good stuff. And hopefully you guys enjoyed this video. Ask questions in the comments.